Hello together, my name is Markus. I've been software developing for almost 30 years now, so I have no clue about a lot of things. And I work at Bertrandt. We have a booth right over here in A4, and I like to show you a real-world example of what we did in a kind of research and promotion program. So, we had a mission in our research programs. As this does not work, I will walk around. The mission was for COVID pandemic to have a safe journey from your home to your car or train, whatever you use to get to the airport, have a safe flight departure, and get in your hotel in a clean, hygienic way without too much of a hassle. And a problem there is one side, the airport side, which we were connected to, and of course cabin side. And we were responsible for cabin side. We were in a research project, as I said, so we had a lot of partners that you see here. We did not work on it alone. So, our task, once again, what we have to do, we have a gate, the boarding bridge, where the passengers come to the airplane. There we had some kind of traffic lights, and then the passenger boarded the plane. Throughout there we had cameras, and we had to connect to the airport so that we know the aircraft is boarding is due, people are still coming, gates are not closed. And we also had some information of congestion state from the gate. So, what we then did do, we toggled this traffic camera. First element that toggled it was the congestion at the gate, of course. If there's congestion at the gate, perhaps you can relieve it by letting the people inside the airplane. The other element we had were the cameras here, where we detected the passengers in their eye, I come to that a little bit later, and tracked them. So we knew they are walking, they have a certain velocity to get through the airplane, and if that stopped, or there were a lot of passengers in the airplane, we just set the traffic light to red. This was also a rule-based element, so we could change the rules as needed. And we were connected to passenger apps, so every passenger knew, okay, my flight is due and boarding will take a longer time or shorter time. And it was also output for the crew, so the crew knows stop or go if they don't see the traffic lights or no traffic lights are integrated. And also we have to be integrated in a real aircraft server that's in the aircraft, that's airworthy, so this was an additional challenge. So what did we do? We started from scratch. So first we thought about how to structure the element. So we said we have some kind of controller unit because you always need that if you are interacting with outside world, like the airport or the gate. And then we said, okay, we break it down to functional areas. We had the camera that processed basically the feed from the camera, normalized the pictures, and put it in some way that we are able to process it. Then we had detection, tracker. We want to track the passengers, you know the speed is quite important. And we have some analyzer to say there's a congestion or not. So this was our architecture. It was just a breakdown. So no UML graphics here, just a functional breakdown. Next, we have a lot of partners to talk with. We are in an aircraft cabin, so we have no landline. We have some Wi-Fi capabilities in the aircraft cabin, but it's limited. So what we try to do, we find a communication means. The communication means needed to be integrated in our cabin server, so it had to be lightweight and efficient, because this is not the fastest of all computers, right? It must be scalable if we have more cameras, and it must be reliable and well supported. And also we wanted to integrate our other communication partners. We decided for using MQTT. So we used the Eclipse Mosquito server as a broker, and we used libmosquito for C++ publish and subscribe. We then implemented a facade to airport systems, so they were usable for us and other partners. And we had configuration for topics with JSON, which we shared with all the other stakeholders. So they could basically ask what is your status, what is the gate status, what flight are we talking about, what is the boarding time, on and on and on. The next problem we faced was that we had a variable numbers of cameras. That was one topic we set out. We wanted to have an unlimited number of cameras supported depending on the aircraft. So we could not deal with a fixed configuration. We had cameras, and for each cameras we had detectors, trackers, and analyzer. How did we tackle that? We said we have a controller. The controller starts up all the nodes and managed states, like we are boarding, we are resetting, boarding is closed, gate is opening, and something like that. And we put the configuration for that in JSON, had a lot of abstract nodes that were configurable using the JSON configuration, and exchanged their data and configuration with MQTT. So no fixed handshake protocol that we had to manage. When we then had these set up for communication and we know how to configure our data, we had to tackle the video processing. So what we do, we have a camera that captures, so we used FFmpeg and the libAVR library. That is basically the library behind FFmpeg. And for image modulation, we used OpenCV. Then we had to capture from the streams pictures. We had to make sure that it's all synchronized, and we had to normalize the data. All this was done also with OpenCV. And after that, we had to detect the passenger. So we used the OpenCV DNN module to have a neural network model integrated. What we chose there at first was a mobile net SSD model, so a single snapshot model. And then we implemented a passenger tracking. Due to performance issues of the server, we had a proprietary Centroid tracker. So what's a Centroid tracker? If you have a frame and you have a weight of the frame, like the middle point, you can calculate it as a Centroid, and the Centroid moves with the position. And you can track this position of the Centroid, and you can track the passenger movement. But keep in mind, we're in a cabin, and the cabin has a flight, so it got smaller and smaller, that frame. You have to keep that in mind. So how do we do that? We had some challenges there. If you look at a cabin, people are always in a line. So some passengers occlude and disrupt other passengers. You cannot see them. I feel like I'm in front of someone that is 1.50 meters, you won't see him on the camera. And we had a viewpoint at the passenger's back. The cameras were in the entry and in the walls, in the ceiling of the aircraft, so it was always looking at the back of the passengers. So not normal people detection there. Also, we wanted, of course, a high precision, high accuracy, so no false positives and as many positives as possible. And, of course, we wanted to have a low inference time. If you wait for 10 seconds while the passenger cabin is boarded, it's no use after all. You have to have that in real time. And, of course, low intersection, so this is a little point there. Also, and this is a big point, it had to be compatible with the OpenCV because we chose that at the beginning. So we used at first the pre-trained mobile net, as I said before, from the CAFE framework. That worked quite fine. So we had like a fluid detection, but tracking and occlusion was not that fine. So we did some transfer learning using the common objects in context database for pictures. And then we had a larger hit rate, basically, for the tracking. A problem we then had, it still was not fast enough. So we tried to have it a little bit faster by training a known model. You just only look once model using PyTorch and exporting it. Nevertheless, this was a real problem that occurred because it was not compatible with the development frames of the OpenCV. This is a really big problem there. We did not solve it at that point. We agreed to move the mobile net SSD and make measurements with the YOLO model separately so we know what could be reached with another framework. So then the problem is a cabin is quite large, and as I said, you have occluded passengers. So we tried to tackle that with a variable number of cameras, as I said before. So each camera defines a section of the cabin. You have 1, 2, 3 sections here by 3 cameras. And then we can detect congestion by Parks numbers and velocity in each section. As we do so, of course, we have to have some kind of summary information. What we wanted to have is no source code for analysis. This was quite important for us. So what did we do? We said, okay, we want rule-based analysis from the MQTT data. Every data is published on MQTT. So we had an in-source script engine using the Wren script language. Don't mind the English, it's just a silly name. It's Wren. Yeah, okay. And for each section, we ran an analyzer. And the analyzer then had the data published also in MQTT. And with the MQTT data, we made a finally stop-and-go decision. And of course, this was once again published in MQTT, so any application could use it. We had a little node here, Node-RED web GUI to show that. And the next thing was the cabin hardware. So we had a cabin hardware from Airbus. We had access to that. Airbus was supporting us there. And the server here has some kind of virtualization. However, the virtualization is not the fastest one. It's not a high-performance server. And you have no access at all to the graphics card, which is the problem with AI detection, object detection. But nevertheless, we had that. And how did we bring it there? We had a Dockerization. So every node that I showed you before, we put in a Docker, also the MQTT. Then we composed the system using the Docker YAML. So we can compose it as many camera connectors, detectors as we liked. And then we just put it on the system and controlled it with a web API that was also using MQTT. And so you can see there's a lot of configuration data on the left-hand side. In the middle, there's the traffic camera, the traffic application. And right, you see from 2 cameras the people that are tracked. If you look very closely, you will see that people on the right-hand side are not tracked. This is because we did limit the detection space to inside the cabin. We have no need to detect any passengers outside the cabin. During boarding, this would be possible, but why? So, to conclude, what did we learn about it? First thing we did learn, we were a little bit surprised because we are not the AI specialists at that time. It was not a daily business. We choose C++ because it's quite fast, but it was a good idea. Not a good idea. Basically, Python is the major choice there. It was a research project for us. We had some trainees working on it, and it was a great value to do that. But nevertheless, we could have done better there for next version. Also, OpenCV is a no-go. It's really nice. It's a really nice framework, and it does a great job at image modification, and we use it for that, but not with the OpenCV DNN module, because this always lags behind the versioning of the frameworks. So no, it's basically not possible to have an up-to-date framework within the OpenCV. So we would do that otherwise. Then what would have been more focus on would be to optimize the model. We had a self-trained model. We did a lot of work there, but we could have started earlier with that and got rid of the OpenCV. But well, it was a research project, you learn. And also, even if you're inside the airplane, one should use a dedicated hardware with access to the GPU, because we reached some live value, so we could really detect boarding and congestion. It did work, but it was like not so fast as we liked. Like we aimed for 30 frames, and we got a little bit less. So I have a video embedded there that I like to show you, that you have some kind of idea what it's about. And we could play that so you have an idea what it's about, if it works. So keep in mind, this is also the work of all the partners. So it shows the system setup, and here we have a screen that is flight safe. This is a rail boarding. We could use it in a plane. We could take off with that. We did not have a flight. This was a little bit problem, but we had a mock-up. And here we have the gate. Also on the gate you have detection here. One of the partners also did ultra-wideband detection. So it's not only camera. As you can see there, passengers are detected. And this was the element that triggered the gate. And you say there's distance below a threshold, so camera is turned to red. After that, you enter the cabin, well, the mock-up, and there you see you have a tracked centroid, and people are entering there, and you can see how many people are in the cabin, and if they are moving or not. Of course, if they're not moving, you have to dedicate that it's what is the ceiling, what is the aisle, where to detect movement. And also, you have a little app here for the cabin crew that they know what is the boarding progress and how is the speed going on, is there any congestion, and how is the status, so it switches to red here. And of course, there were people working on it, and very nice students that agreed to board the plane a lot of times while never taking off, poor people. Really important that it's retrofit with airworthiness. You have the ultra-wideband, and then you have basically the hardware showed there. Do we still have the time to let it run for the last 2 minutes? Okay. So this was provided by the HAW and the TU, the Technical University in Hamburg. They provided the mock-up and did all these modifications to the cabin. So you have the camera in the ceiling. I said 2 cameras, but the 2 cameras set up for test. And there you have the actual cabin server with the Wi-Fi. Here you could directly modify the configuration data in the MQTT, so it was a live update, but of course not live reconnection of cameras, because you cannot install the camera with an app. Yeah, and these were the partners. So, any questions?
Yes, thank you very much, Markus.
There was a question there.
Yes.
It's a little bit difficult to see with the light here.
Where do you collect your data from?
We had students to get it there, to get live data for the boarding. And for the training, as I said, we had the COCO model. So it's basically from the COCO and COMO collection. That is a free collection. But we did not have any licensing for the data in specific, as it's free license. Where they get it from, I hope their legal department is very well working.
Okay, any more questions?
Over there.
All right,
All in the back.
I'm coming.
Is in-flight analysis of suspect persons possible?
This was not a topic here. I think in-flight monitoring, there's also a legal topic with data protection, so one has to agree to that system. I have to get back to the question, what is a suspicious person? You know, if a person just looks suspicious or is nervous or something like that, it's not automatically suspicious, so I would not like to do that. If the person on the other side is randalling about and throwing things, you don't need an IA to recognize it. So, sure, you could do something, but this was definitely not our topic.
Okay, thank you very much. Any further questions from the crowd?
Once again, here.
Yeah. How big has your model been, or how large were the servers?
You mean yet in a size side? Like the
Like
whole on the whole server we had like 1 gigabyte of data, because there was a little bit more to it due to the airworthiness.
But you've trained your model, and how large was the training server, or how large were the capacities you had?
Oh, it's an old i5. So
Okay.
yeah, around that, like it's really not that capable. This is what I said. We reached about 16 to 70 frames with that service and with Docker, without graphics. So I'm quite happy with that. But of course, with a dedicated server with a little bit more power, that would be better.
Okay, perfect. Thank you very much, Markus, from Bertrandt. Where can people find you?
We are just here behind that wall at booth A4.
Perfect.
And my colleagues will look forward to see you.
All right, thank you very much.